Okay, so let's apply what we know about this then. Without looking at the graph here, what I want to know is what is the limit as x approaches infinity for g of x here. Okay, if we look at this function, we can see that the leading term is a quartic function. True? So if it's quartic and the 2 is positive, which it is, then this had better go to what? It better go to infinity. Okay, quartic functions are going to go to infinity at infinity. And when we have a limit as x approaches negative infinity, okay, what do quartic functions do at negative infinity? As we go off to the left, this function, is it going to get bigger or is it going to get smaller? It's going to get bigger also. So again, without even looking at the graph, we don't have to punch that in the calculator and graph it. Okay, we can tell what this is going to act like when we approach infinity or negative infinity just because of the fact that we know about its leading term. Okay. Now again, what does it do around the origin? Okay, that's something we'd have to investigate differently. Okay, but we know what it does at infinity and negative infinity just by the leading term. Okay. Okay. Now, one of the things that we're going to spend quite a bit of time on here in the second, or the next part of this, is to find zeros of polynomial functions. Okay, and we know how to find zeros of linear equations very easily. We can solve a linear equation by setting the linear part equal to 0 and solving that. That's a piece of cake at this point for us. We've been doing that since algebra. Okay, we've also been solving quadratic equations since algebra as well. So hopefully we have that down by either factoring or using the quadratic formula. Okay, we also learned completing the square technique, which we could use if we need to. Okay, but what are we going to do though if we have a situation like this where it's cubic? Because at this point we don't have a whole lot of experience solving cubic equations, do we? Okay, or if it was quartic or quintic or something, a higher power. Okay, what's going to be our general procedure for finding the zeros of a polynomial function? Okay, so like I said, if it's quadratic or linear, we already have methods for that. We're good there. But if we have a situation like this where it's cubic, what do we do? Well, we're going to see quite a few different ways that we're going to handle this. But the first thing that we want to look for is there a way to factor, okay, the polynomial? Because if we can factor it, okay, just like a quadratic equation, we can use the zero factor property. Okay, set each of the factors equal to 0 and solve them individually. Okay, so that would be the best case scenario, is if this were factorable. Well, the first step in any factoring problem, remember though, is to look for a GCF. And in this case, what do these numbers have in common? They have a 2. They also have an x in common, which is nice because what that does for us is if we factor that out, we're going to get that left over. And remember, finding the zeros of a polynomial means finding when does that equal 0. What x coordinates are going to give us 0 when we plug them into this equation? What's going to make that sentence true? Okay? And remember also, when we find the answers to this, they also correspond to the x-intercepts of the graph of this function. True? So knowing that, before we even do this, could we just graph this and find the x-intercepts then? We could. Okay, one thing that we, if the x-intercepts are nice, if they're whole number answers, then we could probably find them easily with a calculator. True? But what if they're not? Okay, then we need some other techniques. Okay, and this is one of them. Okay. Remember that once we factor that, if we're lucky, that quadratic that we get left over will factor also, and in this case it does. We'd have x minus 3 and x plus 1. Okay. And then to find the zeros of this one, and this is a nice one because the zeros are whole numbers, or at least fractions. In this case they're whole numbers, even nicer. So just like we did with quadratics, if we take the 3 parts and we set them equal to 0, then we're going to get 3 solutions here. We're going to get 0 if we divide by 2. We're going to get 3 if we add 3, and we're going to get negative 1 if we subtract 1 from both sides. All right. And remember when we talked a few minutes ago about cubic functions, we said that there are at most n zeros. Okay, in this case we found 3 zeros, didn't we? Okay. Do we have to find 3 zeros every time we do this? No. Okay. Think about what situation that would be very similar to this where we wouldn't find 3 zeros. Let's say we had factored this 2x out. That's going to guarantee that we have 1 0 at 0. True? Okay, but if that quadratic was left over, if this was a quadratic that had only imaginary solutions, that had a negative discriminant, wouldn't we get no solutions from that? We'd get no zeros, would we? Okay, we could find the answers with the quadratic formula. They'd be both imaginary though, wouldn't they? And remember, if they're imaginary, what would that produce on the graph? Would it produce an x-intercept? No. So in that case, it might look something like this then, huh? Maybe we have something like that, where there's 1, 0 that we can see, and the other 2 we wouldn't be able to see on the graph, would we? Okay. Again, should we still be able to find them? Find the imaginary ones? Yeah, we're going to mix that in as we go. Okay. All right. Next. This is what I was talking about earlier with that idea of the graph touching the x-axis and going back down, in that picture I showed a little bit ago. Okay. What it boils down to is that if we have a polynomial function, okay, and there is a factor that has some power to it, okay, then we say that C is a 0 of multiplicity m. Now, let's take a look at where that might occur. If I were to, let's say I had a function that I was able to factor down to x minus 2 squared and then x plus 1. Okay. So if I were to factor that down there as such, okay, keeping in mind that that would mean that I would have a 0 of negative 1. Negative 1 would make this equal to 0. Okay, 2 would make it equal to 0, but remember this has got a power of 2. There's 2 of these. If I were to write them out in expanded form, it would look like that. So both of these factors would give me the same answer. True? All right, and so therefore we would have negative 2. We would write it as such. We'd say the zeros are negative 2 multiplicity 3, and we'd say negative 1 multiplicity 1. Okay. All right. Whoops, I lied. Multiplicity 2. Sorry, there's only 2 of them, not 3 of them. Sorry. Okay, so we'd say there's a 0 of negative 2, it has multiplicity 2, and negative 1, which has multiplicity 1. And if you add the multiplicities together, we ultimately are going to get, in this case, 3, because the overall degree of our polynomial is degree 3. Now, I want you to take a look at the graph of that equation. If I do x minus 2 squared times x plus 1, here's your negative 1, as I mentioned, right? Okay, notice what's going on the graph at 2. Okay. It just touches the axis and goes back up, doesn't it? Okay. Is that going to be the case always when we have multiplicity 2? Maybe. We've seen a couple cases so far where that's worked. Okay, let's carry on. Okay. And this slide kind of tells us what the deal is with that question that I just asked. If a polynomial function has a real 0 C of odd multiplicity, okay, then the graph of f crosses the x-axis at that point. Okay? So if it's odd multiplicity, like 1 for instance, okay, then the graph is going to cross the x-axis. It crosses it at the point C0. Okay? And the value of f changes sign at x equals C. Okay? So in other words, the function changes from positive values to negative values, or vice versa. Okay? And if we have a polynomial that has even multiplicity, like that one I just showed you a minute ago, okay, then the graph does not cross the x-axis at that point. Okay? And the value of f does not change sign at C. Fair enough? Okay, so if it has even multiplicity, okay, it does not cross the x-axis. It hits the x-axis and goes back. Okay, either back down or back up, depending on where it's coming from. Fair enough? Okay. All right. So looking at this one, let's see if we can figure out what's going to happen here. So if we have this one, we would say that this has a negative 2 multiplicity what? Multiplicity 3. And this would have a 1 multiplicity 2. Overall, it's a 5th degree function here. This would be cubic and quadratic, and if we squared them, if we expanded that all out, we'd have an x to the 5th term here. Keep that in mind. So that means the end behavior would be, notice that these x's are always going to be positive, so the end behavior would be something like this. Okay, down to the left, up to the right. Okay. So when we have negative 2, at negative 2 we have multiplicity 3, at 1 we have multiplicity 2. So on the graph, if we were to look at that, okay, the negative 2, we do cross the x-axis. Okay. Notice with the multiplicity, it's instead of just straight up crossing it, though, there's a little bit more action going on there. True? Okay, but at the 1, we're at multiplicity 2. What does it do? It doesn't cross the x-axis. It comes down and then goes back up. Okay, and of course it does have the same end behavior that I mentioned earlier, doesn't it? Because it's a 5th degree function. Okay. So if we see a picture like that, okay, and we see that particularly, we should know that that must be a 0 that has even multiplicity. Okay. This one would be a 0 that has odd multiplicity. Questions so far? All right. Now, one other theorem that we have here that we're going to look at is what we call the intermediate value theorem. Okay. And this is a kind of a complicated set of words here that's in your book and on this slide as well. Okay, I'm going to make it simpler for you here in a minute when we look at the picture. But here's what the intermediate value theorem guarantees, that if we have a continuous function, and this is probably the main part that we want to make sure we're clear about. Okay, this is only true if we have a continuous function. Okay. And I'm going to go right straight to the picture here. Okay. What the intermediate value theorem guarantees us is that if we are at the point A, f of A, if we're at that point right there, and we go to B, f of B over here, okay, and the y-coordinate at A is negative and the y-coordinate at B is positive, then at some point between A and B, we had to have crossed the x-axis. Okay? So think about how that might look. If I told you that f of negative 2 was negative 5 and that f of negative 1 was 6, okay, then what had to have happened between negative 2 and negative 1? If I go from y-coordinate negative 5 to y-coordinate 6, okay, the intermediate value theorem guarantees that I cross every value between negative 5 and 6. And what value is important between negative 5 and 6 for us? 0. Okay? So this would be a guarantee. As long as we knew f was continuous, okay, and we had this information, then we could say for sure that there's a 0 between negative 2 and negative 1. Okay? Now, would it be true going the other way if I said f of 3 was 5 and then f of 4 was negative 6, let's say? Okay. Is it okay to go from positive to negative coordinates, going from left to right? Certainly. Okay. This would also guarantee, again, as long as we knew f was continuous, this information would be enough to guarantee that somewhere between 3 and 4, okay, we crossed the x-axis because the y-coordinates went from a positive to a negative. And again, what important number is between positive and negative? 0. Okay. So there had to be a 0 between there. So again, that intermediate value theorem guarantees that that's going to be the case. Okay. All right, one last part I want to look at